Thus far, our analysis is just focused on two force members where we will just have an internal tensile or compressive force. If, however, we load trusses um, and apply loads that are between the ends, somewhere in the middle, then we actually get sideways or shear components of force. So it's not just a two-force member anymore where the force is along the structure, there's a sideways component, which is called a shear force. So let's see how we would analyze that. The good news is it's really just going to build on the equations of equilibrium and the idea of making a section, this time not through the structure, but this time just through this single structural element. So we're asked to find the tension, shear force, and something called the bending moment. Now a bit of notation. Tension is N, shear force is V, and bending moment is M. And we want to point 3 meters from the left end. Okay, so it's about here somewhere. So at this point here, we want to know what are the internal forces at this point. Okay, well, the starting point is still the same, i.e., we're going to analyze external forces. So we need a force diagram to start with then. So what forces are acting here? What reactions do we have at the supports? Okay, so there's a roller joint at B, so there'll be an upwards force at B, and then there's some sort of pin joint at A, so we could have a Y component and an X component there. And so we want to do equilibrium analysis to find out what these forces are, AY, AX, and just B. Okay, well, the conditions for equilibrium, some of the X forces have to sum to 0 because it's an equilibrium, so we've got positive AX and positive 100, so clearly we know AX is simply going to be to the left, 100. Summing Y forces, we've got upwards AY, upwards B, and downwards 200. So that can't be solved, so we need a moment equation. Let's sum moments about A. So this 5 meter distance is to the point of application of this force. So we've got, with Z coming out at us, this will be a negative moment, 200 newtons, 5 meters from the point A. And then we've got a positive moment from the B reaction force, 7 meters from the point A. Moments sum to 0. So we can solve then. And we find the force from the B is a 142.86 newtons, 57.14 newtons at AY, and then as we said earlier, AX is to the left, 100 newtons. Okay, so we've done that many times. So now what's different? Well, now we're going to go inside that structural element, and we're going to cut it right there. So somewhat similar to the method of sections, and then we're going to consider the forces on both sides of that cut. Now, there will be 3 things to consider. First of all, the component that's along the member, and that's called the tension or compression force, and that's an N. And we will assume that both of these members are in tension, so the N force will be pulling this part of the section. So this thing in gray, this is here, and this is where the cut was made. So if I call this point A and this point X, right? So this is AX and this is XB. Okay, so we'll assume that it's in tension. And if you just sort of, not even worrying, well, if you just took this beam between A and B and you push down on it, then you're going to be stretching it out a little bit, and so therefore inside there's going to be tensile forces, right? Just pushing down on this is going to tend to make it sag a little bit and stretch it all out, and so it'll all be in tension. So that means there'll be the XB side will be pulling on the AX side to the right. That's what this internal force is. Now, as this sags, that means this side is actually pushing down on AX. So this is a positive shear force. And there will be a reaction force acting on the other side. Finally, the tension force actually varies over the cross-section of the structural element. You can understand that if this beam is sagging downwards, as it is going to do at the point X due to this applied force, that this bottom part's actually going to stretch a little bit more than the top part. So there'll be a slightly larger tensile force here than the top. This top might actually be in compression. But even if it was still in tension, if this tension force on the bottom, there's a little bit more stretch on the bottom, therefore a little bit more elastic force, if that one on the bottom is greater, then there's actually a moment there. And that's called a bending moment. And so we will, and you can see the direction of that moment about the point X, right, is going to be in the positive Z direction. So a positive bending moment will be in that direction. And if this one tends to have, due to the inhomogeneity and tension force, a positive Z moment, there'll be a reaction moment on this one, which will be negative. And you can see, just using the right-hand rule, that this one is negative and into the page. So, applying that then to our force diagram, so this is the point A, this is the point X right here, where the section was made. So the AX segment is pulled to the right by the XB segment. It's pushed down, I should label that as N. It's pushed down by the XB segment. And then finally, what we've drawn here as the tension is actually just the average tension. The tension is actually a little bit bigger on the bottom than it is in the top, and that gives us an anti-clockwise or positive bending moment. So the AX segment is pulled a little bit more at the bottom than it is at the top, and so that gives us a moment M at that point where we made the section X. That's our sign convention. Now, having drawn those internal forces in, we then simply apply the equations for equilibrium, either to the left half or to the right half. So we had previously found that there was the upwards Y force of 57.14. And then this was AX, and it was 100 to the left, so I've just drawn it 100 this way. And so then let's label these. N is to the right, here's the reaction moment, and then here's the shear force. Okay, over here, B was 142.86, and then these would be the reactions. Action-reaction pair, action-reaction pair, action-reaction pair. Okay, so let us consider the AX segment and apply the conditions for equilibrium. So X forces sum to 0, so we've got positive N and minus that the tensile force is 100 newtons at this point, 3 meters away from the pin joint A. Summing Y forces, we've got upwards AY, and then we've got downwards shear force. Those are the only two. So now we know how much the shear force is. It's downwards 57.14 at that point. Then let's take moments. Now you could take moments about any point, but it's conventional to take it about the point where you've made the slice, about the point X, because then you don't have to worry about moments of N and V. So about this point, the only thing that gives you a moment here will be the Y component, and using the usual coordinate system, that will be like a into the page or a negative Z moment. So that's the AY force, the 57.14 newtons, and it's 3 meters from that point X. Now, what is balancing that out? Well, that is this reaction moment, this internal bending moment. So those are the conditions for equilibrium. Those are all the forces and moments that are acting on this piece. And so now we can solve. These equations are fairly straightforward to solve. So we get, first of all, for the bending moment. Okay, sorry, sometimes my tablet acts up a little bit, but there are the values at that point 3 meters from the pin. Now notice that if we had analyzed the equilibrium of the XB piece, that was the piece down on the right end, these are the equations that would result, and you get exactly the same solution. So what that solution is telling us is this is in tension. So at this point right here, this piece is being pulled to the right by the XB piece. So AX is pulled to the right. AX is indeed pushed down by this piece. and it also experiences a moment due to the inhomogeneity in the tensile force. And that moment's called the bending moment. So these two forces and this moment are internal. They're due to one part of the structural element pushing and pulling and torquing another part of the structural element. Let us, instead of focusing on the point 3 meters from the pin, let's now let that distance be a variable. And then we can see how those internal forces vary along the length of the structural member. So instead of making a section at a distance 3, we now make a section at a distance x, where x is obviously a variable. We do need to consider two cases. First of all, for x less than 5, so we're this side of this point applied force. So at this point, well, first of all, the external force analysis is the same as before. So we know for instance, what the forces at the point A and B are. Let's just quickly put those in. So there's an upwards force here, there's a force to the left here, upwards force there. So this was B, and it was 142 point, well, what did I say? 142, is that say 86? I think it says 86, yeah, 86. And that's in Newton units. So this was a Y, was 57.14, and then this was AX, and that was 100 to the left. Okay, so at location X, we now draw the forces, the internal forces at this section. So we assume that it's in tension, we assume it's pushed down, and we assume that it's reacting with a positive Z bending moment. And so now we apply to the AX section, we apply the conditions for equilibrium. So Y forces sum to 0, X forces sum to 0, and the moments about the section also sum to 0. Well, this is going to be, at the start anyway, quite similar to what we had before, because I'm now going to, so in the, say, the Y direction, so we've got upwards 57.14 and downwards V, then we've got tension to the right and 100 newtons to the left, and then moments about this section X, so we still have 57.14 newtons, but now the distance to the section is no longer 3 meters, it's a variable X. So that's the moment of the AY force about the section, and that must be balanced out by this internal bending moment. Okay, so solving that now, well, the shear force is the same as what we had earlier, as is the tensile force. But now the bending moment, we can see, depends on the distance x, and it varies directly with it. Oh, I forgot to mention, of course, there's something that's missed here, that this was a negative moment because it's an into the page negative z direction. So that's why this ends up being a positive number. So just to finish this off, let's note that the moment increases as we get further from the pin, because it varies directly with x. All right, so remember that was just the first case. We still have to consider the case where the section is made on this side of the structure, i.e. past this point where we have this point load applied. So how does that change things? Well, the external forces, again, are the same. No need to repeat that. We can just put them down on here. So that's 142. This is 37.14. That's 100. And we'll again assume that it's in tension, so it's being pulled to the right by the other member. It's being pushed down by the other member. Well, not another member, but the other part of the structure. And that finally, there's a reaction moment that is positive in the z direction. Now in our force analysis, we will have this 200 and this 100 that enter into it as well. Okay, so let's apply again to the AX section. Just the equilibrium of this piece. You could do this piece and you'll get exactly the same answer. So, X forces. So what have we got? We've got 100 to the left. We've got tensile force to the right, but we've also got the 100 to the right, this point force here. So solving that, we see, hey, there's no tension at all in this part of the structure. It's zero. Okay, how about the shear force? So we've got upwards AY, we've got downwards 200, and we've got downwards shear force. So now we can see the shear. So now we see the shear force is negative, meaning that it's opposite to this, meaning it's actually upwards on this side of the point load. So here it was downwards 57.14. Over on this side, it's upwards. That sideways force is now pushing upwards on this A segment, which kind of makes sense if you think about it, because we're pushing down with 200 newtons here. So the XB segment must now be pushing up to help balance Y forces. Now we'll take moments. Again, we usually take moments about where we've cut it. So the 57.14 AY force is a distance X away from our section. We have our bending moment M, but we've also got this 200 Newton force. So taking moments about the section, the 200 Newton force is an anti-clockwise or positive moment. Now, X is the distance to the section, 5 is the distance to this point load. So this distance here is X minus 5. So the 200 Newton force gives us a positive moment about X. And it acts a distance X minus 5 away from the section. So we have some like terms to add. We got 200x minus 57.14x, and then we got to take that to the other side. So our moment, bending moment, ends up being, in terms of x, this expression right here. So this actually now decreases with x. Now it's customary to represent this answer here for this problem in terms of graphs. And the graph that we'll draw is going to be lined up with the structure. We'll graph the shear force and we'll graph the bending moment. And things change, of course, where that point load was applied. So we'll make sure to draw a nice transition there. Okay, right there. That's where things got interesting, right? Perfect. Okay, move that over a little bit. Good. Okay, so what was the shear force? Well, the shear force was just a constant. And it was a constant positive or downwards value on this side. So the AX segment was pushed down by the BX segment. But then as soon as you passed this point force, then the AX segment was actually pushed upwards. And that's a negative shear force. Now I suppose I should be careful to end it where the structure ends. So let me just drag something over here. There we go. Okay, so that's where our graph should end if we're being picky. And it's important to be precise, I guess. Okay, so putting some values on this. This was the 57.14 newtons of shear or sideways force, constant through this segment. Then once you passed this point load, it was then negative 142.86 newtons of shear force. Now the segment AX being pushed up. How about the bending moment? Well, the bending moment, first of all, increased with X. So a nice straight line. Get a straight line here. Up to this transition point. Okay, so this is the bending moment graph. And the equation of that graph was 57.14x. Now that went up to x equals 5. So if you put 5 in for this equation, you find this value here is 285.7. Now, after that point, the bending moment decreased with x, and the equation was minus 142.86x plus 1,000. Now, if you put in, oh, that's horrible. Okay, I'll rewrite that. But if you put in x equals 5, what you find is that it's the same 285.7 value. So that means that this line starts at the exact same point. And then if you put in x equals 7, you find that the bending moment is dropped back down to 0, which makes sense because we're at the support, so there should be no bending moment there. Okay, so let me now try writing this a little more neatly. 142.86x plus 1,000. Okay, that is supposed to be a 4 and not a 9. Other than that, it's not that bad. So we notice a couple of things. There is a jump in the shear that's exactly 200 newtons, which is exactly the same as that sideways applied force. So the discontinuity in the shear force equals the sideways component of the point load. Okay, so it jumped to 200 newtons at that point. We also notice something else. Like if you look at this graph of the bending moment, notice the 57.14 value and the minus 142 value. And then we remember a little bit of our calculus. We can express that in a really easy way. It looks like the derivative, or the rate of change of the bending moment, is exactly the shear force. Okay, so now it's your turn. So we've set up a similar problem here. And so remember, there's 3 steps here. First, you're going to do external force analysis. Then you'll make a section and draw the internal forces at the section. And then you'll apply the conditions for equilibrium. So we'll do this one step at a time. It's your first problem. So first of all, do external force analysis to find the amount of force at the 2 supports A and B. So pause the video and then do that work. Okay, so let's see how you did. It's pretty clear in this case with such a symmetric structure that A and B are each going to take half of the load, and the load is just this 5,000 Newton force, and there the moment equation confirms it. Moments sum to 0. I did moments about A, you could do moments about B as well. Okay, so that's the first step. Now, having done that, what we do next is we make a section, and so we're going to cut this here, and then we're going to draw the forces on this part and write equilibrium equations. So pause the video and try doing that now. And remember that we're going to have to do a section on this side because there's 2 cases, right? One, we're making the section on this part of the segment. Another one, we're making the section over here. So those 2 cases will need to be considered. Okay, so there's the section at distance x. So draw the force diagram and do equilibrium analysis. Pause the video and give it a try. Okay, so hopefully this is what you found. There's no tension at all because that's the only x force. And the AX segment is being pushed down with 2,500 newtons of shear force by the other segment. And then there's a reaction moment, an internal bending moment, that increases with the distance x, 2,500x in direct proportion. So that was a section on this side. The next thing to do, once again, pause the video, make a section on this side, and then again solve for the internal forces. Okay, so hopefully this is what you found here. So now y forces, because we now have this point load of 5,000 newtons downwards, so the shear force flips direction. So we find that this segment's actually being pushed up by the other segment. The shear force is negative. For the bending moment, well, we had the moment of the A force acting a distance x from our section. We also have to find the moment of this 5,000 Newton force. We should note that that A moment is a clockwise or a negative z moment. This 5,000 Newton force applied to the right of the section, that's an anti-clockwise or a positive moment. Now if this distance x is x and this is at the middle, then our moment arm here is x minus 2. And then of course we have the bending moment. So solving, hopefully you got that. So now the final step in our analysis is just to sketch graphs in the space provided of both the shear force and bending moment as a function of length along the structure. So pause the video and try doing that. So if you sketch those graphs, so we had a constant downward shear force and then a constant upward shear force. Notice that that discontinuity is again exactly equal to the point load. Then for the bending moment, it increased to 2500x up to the point x equals 2, where you've reached a maximum bending moment of 5,000 Newton meters. Then it decreased back down to zero bending moment at the support, according to this equation right here. Once again, reminder that the rate of change of the bending moment was exactly equal to the shear force, and the discontinuity in the shear force was exactly equal to what that point load was. Now, where we go from here is we consider distributed loads, and we see what that does to both the shear force. A little bit of foreshadowing, it's not going to change suddenly, it's going to change gradually, and then what it does to bending moment. A little bit of foreshadowing, instead of being a straight line, it'll be a curve. But that's to come in class. For now, I did one example and you worked through one, so we're off to a good start on this topic.